1b. This is an additional note from Glasgow, and therefore let's do this question, okay? And then it should be very fast. I hope I can clear this by this video for the whole question, okay? So the crankshaft bearing of an automobile engine is lubricated by oil with a viscosity of 9.6 times blah blah blah. So if you remember, this is the engine shaft, and then you have a layer of oil, okay? And then the density of it is actually 920 kg meter cube. And then diameter of the bearing, the diameter of this is actually 0.0762 meter. Okay, and then I think the bearing is actually this one. Sorry, I think this is this one. This from this point to this point. Okay, and then I can actually use this picture. Then why didn't I use this? Easier to show you. And then its clearance is actually A. So this diameter from here to here is actually 0.0762. Okay, and then the clearance is A, which is this one. So if you still remember, this is the shaft. This is the shaft, right? And then you have a bearing. And then in between them it's oil. So when the shaft is turning, there will be the blue one will not rub against the green color because of the oil layer in between. So this is like the grease. So if you want to know more of this thing, you can actually visit back this video, this series on this stuff over here, I think. Okay, so it's actually this one. You can actually head back lah. So it's actually in lecture 6, okay, video 6. So let's take a look. So let's continue first. So if you don't understand this, it's okay, never mind. You go and watch back that one. Okay, I'm not gonna repeat everything. So what do I do now? Okay, so the shaft is actually this amount of length, and it rotates at a certain speed. And then the oil flow in the bearing may be modeled as a blah 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 between two parallel plates. If you don't understand why it's modeled between two parallel plates, if you are looking at a very small infinitesimal thing, you're actually looking at a piece that is really that is parallel. It's a very small piece lah. Okay, it should be parallel. Okay, so this is why it's represented over here. If you don't understand why, go back to that video also. Okay, so mainly is at the very first few parts lah. Okay, maybe this 3 lah. Okay, maybe this 4. I think this this 4. Okay, so just go and watch it. And then okay, what do I do now? So by applying appropriate boundary conditions, derive this thing. So how do you derive? You can go back to this 4 videos. It's exactly the same. If you don't believe, you see the outcome. Okay, the values are exactly the same. I'm not gonna cheat you. Okay, they are exactly the same. U y over a plus y over 2 mu partial p partial x y minus a. Okay, so 5, 4, 3, 2, 1. Okay, done. So yeah, I can skip this part. So let's go to this 4 of it. Okay. So next question. Take the zero pressure gradient. Okay, so I'm talking about this one over here. Okay. Take the zero pressure gradient. Calculate the amount of shear stress acting on the shaft. So pressure gradient is the keyword. 0 is the keyword. So in this case, this term is actually 0. Why? If pressure gradient is equals to 0, the whole equation becomes to 0. So therefore, you know that U is equals to Uy over 8 plus 0. And then you know, so how do you calculate shear stress? Shear stress is equals to mu multiplied by partial U partial Y, right? If you still remember, this is the shear stress. Alternatively, shear stress is also equals to force over A, right? And then this is the shear force, whatever. Okay. So if you still remember, I'm not gonna repeat again. So this is the shear stress formula, please remember. So this is your viscosity. Okay, this is your viscosity value. If you want to ask, it's actually this one, 9.6 times 10. And then this one, you need to differentiate. You know u is equals to uy over a. So partial u, partial y, you're going to get u over a. Okay, so with this understanding, maybe I shouldn't erase all this. I just leave it like that first. Let's go to the stuff. Okay, let's come to here. So this is exactly the same thing that I'm talking about. So this is your viscosity. I should use a red pen. And then if it's 0, pressure gradient, after that we prove that we're already here. Okay, so tau is equals to mu u over a. Okay, so I have done all that much. We have reached over here. Okay, so partial y is actually u over a. So therefore you can replace this as u over a. So mu. So therefore it's the same exact thing as this. Okay, yeah, the same exact thing. So you just sub in the values. Okay, so in this case, u is your angular velocity. So this u is actually an angular velocity, and also can be get from linear velocity. So how do you get? If you still remember, this one is from your previous video. U is equals to omega r. Okay, so u over r is equals to omega. Okay, so how you gonna use this information to help you solve for certain things? So this is actually because you want to sub equation as u, right? So okay, angular velocity is equals to the linear velocity divided by the is it the radius? I think it's the radius. If this doesn't mean rings a bell, you can actually head back to this one. Okay, it comes from a certain videos. Okay, somewhere around here lah. Okay, somewhere around here, this portion over. I mean this top one lah. Maybe in this case, this one lah. Okay. So this is actually linear velocity. Okay, go in this direction equals to omega, which is the angular velocity, which is not shown over here, multiplied by r. Okay, so in other words, this is meter per second is equals to theta over t, because it's omega, it's just an angle per second, multiplied by radius meter. Okay, so this is some radius r lah. Okay, so in this case, it's the same thing that I'm using right now. U equals to omega r. I'm using this one. Okay, so therefore the omega is actually 2 pi 3600, and then the radius is actually this value. How do I get this? If we take a look, okay, it's calculate the amount of shear stress acting on the shaft. So the shear stress acting on the shaft is actually contributed by the bearing. Okay, when it's turning, okay, that's the bearing over here. So this external radius is the bearing. So when this ending shaft is turning, there is a frictional force in between. So this is the oil, right? Then this plate is actually the shaft, and then this is actually the bearing itself. So there will be a certain. So when you're taking the diameter, so you're taking actually the diameter of the bearing. So remember that lah. Okay. So shear stress acting on the shaft. Make sure you take the diameter of the bearing. I have no idea why, but you just take it. So in this case it's radius, so therefore you need to divide it by 2. So in this case 0.06, if let's say I do this, 0.0762 divided by 2, I have 0.0381, which is very well reflected over here, 0.0381. And then the omega is 2 pi times 3600 divided by 60. Why do I do that? Okay, this is 3600 is actually RPM. Okay, if you remember, it says that the shaft it's this long, will rotate at 3600 RPM. So in order to change in terms of meter and seconds, we have to actually multiply by 2 pi, which is the radian per second. Okay, so if you were to do that, you will get some values. Okay, if you were to do something like that, you will get this value over here, meter per second. Okay, so remember, if you have a RPM, make sure you change in terms of 2 pi divided by 60. Okay, this is the key thing you need to remember. So remember 2 pi over 60. Okay. So yeah, so this 2 pi and is actually radian per second. Okay, whatever. So and then what do we gotta do? So if you were to sub in your viscosity, if you were to sub in your this value 14.36 and your R value, okay, which is A in this case, okay, you get this value over here. So let's try. If you were to do that, this is the viscosity. Okay, viscosity, the value is 9.6 times 10 to the negative 3. So in this case, it's divided by 1000 lah. Okay, and then this R, okay, or this A itself. Okay, if you remember how we derive this one, you know that this is U divided by A, right? So therefore, this A is actually the one that I'm talking about, this A. So if you're talking about the R, I don't know where the hell is the R coming from. So it's from maybe from here to here, this is R, but whatever. So the best is to say that this is A lah. Okay, so let's don't confuse ourselves saying that this is R. So we just say that this is A. So in this case, A is 3.17 divided by 10 to the power of 5. Okay, why? Because negative 10 to the power of negative 5. So you just have to divide. So I have this thing over here. So if I were to work it out, okay, so 9.6 divided by 1000 multiplied by 14.36, which is this one over here, and then I multiply by 3.175 divided by 10 to the power of 5. Okay, so this is this one now. Okay, my value will be, okay, something is wrong, but but you should get that value over here lah. Okay, because my calculation, let's do it again. I hate this calculator, seriously. So this is 0.13786. Okay, so remember that. No need lah. And then I multiply by 3.175, and then I divided by 10 to the power of 5. Dun dun, something is wrong. I think the best is actually use Google calculator. Divided by 1000 multiplied by 14.36, and then divided by A, okay, divided by 3.175 times 10 to the power, where's the power of 5, sorry, should be minus 5 bracket, dun 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 dun, 4341.92, so it's somewhere about there. Okay, 434. So Google is much better calculator than this friend over here. Actually, yeah, I'm more stupid anyway. So this is the shear stress of that thing over here. So we calculated our shear stress. And then I've reached 30 minutes. Yeah, so I'll just calculate the other 3 stuff in the next video. So I'll see you there. Bye bye.